Welcome all of you. Almost several weeks we discussed in depth about one-dimensional NMR, right from rudimentary concepts to interaction parameters, multiplicity pattern, chemical shifts, the factors affecting chemical shifts, and how do we get multiplicity pattern when one proton is coupled to groups of other protons, etc. We analyzed lots of one-dimensional spectra of proton, carbon, and various other heteronuclei. Based on the multiplicity pattern, we could get lot of information. How do we make the assignment, everything. And also we could extract the coupling information from between two abundant spins, coupled spins, abundant to rare spin, dilute spin. From the we analyze the satellite spectra. From the satellite, not only we get heteronuclear coupling, we also got homonuclear couplings. And then we extended this analysis further. We understood afterwards about spin echoes. What is a spin echo? How does it happen? I said 90 degree followed by a delay with another 180 plus a delay. It was a conventional spin echo sequence. And the Hahn echo was 90 tau 90 was the tau was this thing which was first given by Erwin Hahn. A spin echo is a time reversal experiment. And we understood how the spin echo works. And we also understood what is a J modulation. What will happen to the spin echo sequence, especially when we have homonuclear spin. What happens when you have a heteronuclear spin? When chemical shifts gets refocused, when J coupling gets refocused or not. All those things we understood. We extended this further for the polarization transfer experiment, where we saw that we can transfer the polarization from abundant spin to rare spin, like dilute spin, proton to carbon, phosphorus to rhodium, proton to nitrogen, like that. And then we can use all these methods not only for polarization transfer, but also for identification of different carbons attached to different number of protons, based on whether the carbon is attached to CO1 proton, 2 proton or 3 proton or quaternary carbon. Using inept experiment, we were able to identify them. We can use it for spectral editing, especially for carbon 13. And the same polarization transfer is used in depth experiment I told you, where, and I said in using depth experiment, we can identify different carbons also. So with the J modulation, we understood APT, depth, inept, all experiments we understood. Of course, depth and inept are polarization transfer, but APT is not. It's only a spin J modulation experiment. But all these things can be utilized for identification of different carbons plus polarization transfer. So a lot of things we understood about 1D NMR, and we spent several hours on that. And now it is time to go for a advanced experiment, advanced subject called two-dimensional NMR, where we can use this method for further simplifying the experiment or further simplifying the spectra, for aiding the analysis of the spectra, getting more information which you cannot get from the one-dimensional spectra. So a lot of things one can do. So we will start from today, two-dimensional NMR. Of course, two-dimensional, there are several experiments. There is also one experiment called 2D NOSI. I will introduce before that a concept of NOSI. So I have not introduced yet, but I am going to introduce it later. But right now we will start with the 2D experiment. Okay, with this, let us see how it goes. We will ask a question: what is 2D NMR and why it is needed? This is the first question we have to ask. What is a 2D? Why do you need 2D NMR? First we have to understand the limitations of 1D NMR. What are the limitations of 1D NMR? Depends upon the size of the molecule. What happens? So far we analyze only small molecules, small organic molecule spectra, small molecules for heteronuclear spectra, etc. That is fine. But what happens as you go to bigger and bigger molecule? Take for example a big protein consisting of, let us say, 10 or 20 amino acids. Each amino acid running from CI3 to NH proton, so many protons will be there. Each of them form a spin system. So many peaks will be there, and they will all be overlapped. And the proton spectrum will be within only 0 to 10 ppm range. Then what will happen? So many peaks overlapped, so complexity, it is very difficult to analyze the spectrum. So what it means, as the size of the molecule keeps increasing, the number of transitions and the complexity of the spectrum keeps increasing. Of course, assuming the symmetry is not there. If the symmetry is there, higher symmetry, then what will happen is number of transitions get reduced. Spectrum becomes less complex. That is well known. But basically remember, for the 1D NMR, there is a limitation for the size of the molecules. As the size of the molecule keep becoming bigger and bigger, spectrum becomes very complex. So that is one limitation. Second, assignment problem is due to spectral complexity. So far we were analyzing the spectrum very easily. I used to say that CH3 proton, CH2 proton, CH2 is a triplet because of CH3, CH3 is a triplet because of this. All those things we were able to analyze. Which is quartet, which is triplet. This is quartet because of 3 protons, equivalent protons, and this is triplet because of the 2 equivalent protons. All those things we knew and we are able to assign. It is a straightforward, easy way of analysis. This is a straightforward analysis, simple analysis. This is possible only when the spectrum is not complex and well dispersed. If you go to a simply bigger molecule, slightly bigger molecule with an enormous overlap and spectral complexity, you cannot make the assignment in so easy way, because each proton, let us say I showed you one example of a case where one phosphorus was having 4 different coupling and gave 90 peaks. Like that there could be enormous complexity, in which case assignment of the peaks for a particular chemical inequivalent spin is a very, very challenging task. And next is, it is not possible to separate the interaction J and delta. Remember, chemical shift and J coupling will be present both simultaneously in a 1D NMR. I took 1D NMR spectrum, and when we analyze, we say chemical shift here, but that is also having multiplicity pattern because of J coupling. So both are present. You cannot separate them in 1D. Okay, so it is very difficult job. Because when you separate these two interaction, your spectrum analysis becomes easy. There is a lot of simplicity will be is there in the spectrum. So this is a big issue, and this is one limitation. And you cannot correlate the interactions. For example, if I want to say CH3 proton is coupled to CH2, how did I understand that? Based on the multiplicity. I know this CH3 is a triplet because of CH2, CH2 is a quartet because of CH3. I know multiplicity. I can correlate. If there are enormous complexity there in the spectrum, how do you even extract the multiplicity pattern? How do you do the correlation? Not easy. Let us say one proton is coupled to several other protons in different groups with different chemical inequivalent protons, and there is everywhere there is a overlap. How do you identify that? So which is coupled to which is very difficult to correlate. So these are some of the practical limitations of 1D NMR. Continuing further, there are forbidden transitions which you cannot detect in 1D NMR. I told you selection rule is delta M is equal to plus or minus 1. Change in the magnetic quantum number between 2 spin states either should be plus 1 or minus 1. Anything above that or below R0 is, they are called forbidden transition in NMR, and you cannot detect it. It is not possible to detect. So that is one limitation. Another thing is simultaneous detection of different nuclei is not possible. That is another very interesting thing. For example, if I want to take a 1D NMR spectrum of proton, I have to tune the probe and do the experiment at, let us say, 400 MHz spectrometer. At 400 MHz I will put it, I get only proton signal. If I have to do carbon 13 NMR in the same spectrometer, I have to do some changes, like I have to change the frequency of the probe and transmitter, receiver, tune the probe, everything. It is not easy. You cannot get everything so easily. You have to do some changes and then see the carbon 13 signal. But both simultaneously you cannot detect. At the same time, I do one experiment where I get carbon signal and detect carbon and also proton. Not possible to do. These are all limitations of 1D NMR. It puts you some constraint. So how do you overcome this? And first of all, what is 1D? Okay. After understanding limitations of 1D NMR, let us see what is a 1D NMR means. We have been analyzing all along since several weeks. They are all 1D NMR, one dimensional NMR. What do you mean by one dimensional NMR? This is a simple experiment which I told you. Apply radio frequency pulse and start collecting the signal. Oh, this is called a dead time delay. You don't worry. These are all not discussed in this course, but in the previous courses I explained this. So this is apply radio frequency pulse and start collecting the signal as a function of time. And then after collecting the signal, what we do is we do the Fourier transformation. When you do the Fourier transformation, what you are going to get is a spectrum like this. Very simple. This is a conventional one dimensional NMR. Apply radio frequency pulse, collect the signal and do the Fourier transformation. And here you have the intensity, and what you have here? Chemical shift, frequency. Okay. Or in other words, I can in a short way I can put it like this. There is a delay here. This is called a relaxation delay. Before you apply a radio frequency pulse, after putting the sample in a magnetic field, you have to wait for some time. Or after you apply a radio frequency pulse, before you apply another pulse, you have to wait for some time. Because the spins have to come back to thermal equilibrium. They have to attain equilibrium. Only then you can apply another pulse to get maximum signal. And this is called a relaxation delay. The spins take some time to relax and come back to thermal equilibrium. And that I call as also as a preparation period. I am preparing the spins to get the signal. This is called a preparation period. Okay, where spins are allowed to relax and attain thermal equilibrium. And this is where I am collecting the signal is called a detection period. It is called detection period. And now you understand one thing. In this 1D NMR experiment, what we have is signal is detected in the one time period, and you do the Fourier transformation and you get the frequency. That's all. So what does it mean? One dimensional NMR means you collect the signal in one time domain, do the Fourier transformation and get the frequency spectrum. This is a one conventional simple one dimensional NMR. Then what is a 2D NMR? A general pulse sequence for the 2D NMR is given like this. What did we saw? Here one thing I wanted to tell you here, you must understand we have a preparation period and a detection period. There are two things which are present in 1D NMR. Go to here. As always there is a preparation period. That is a period where you allow the spins to come to thermal equilibrium. Fantastic. Then we are going to have, have another time period called T1, it is evolution period. Another time period called detection period, it is called T2. We have a mixing period in between these two called, some optionally we can use it whenever we want for some specific experiments. Okay. And after the preparation period, I am going to apply a pulse P1. A pulse, some 90 degree or whatever the angle, I apply a RF pulse here. Then I will allow the spins to evolve with time. Spins are evolving after 90 degree pulse. What do you mean by evolution? Spins start undergoing evolution because of chemical shift, J coupling, etc. where precision can be there. Spins, there could be free precision after the pulse because of chemical shift and J coupling. Okay. And then what I am going to do is, this time I do not keep it constant. I can systematically vary it. Every experiment, I keep this one constant and then collect a signal. I will go further. And here we have a mixing period. I will come to this later, I will explain. I have a mixing period where information is transferred from one spin to another spin. There the information is relayed, taken from one spin, give to another nuclear spin. And apply another radio frequency pulse. This is called a detection pulse. We apply to detect the signal. Then you start collecting the signal like we did in 1D and do the Fourier transformation. Now this is a constant period, no doubt. But this one is not a single period. This is one experiment. I keep this T1 constant, do one experiment. What I will do, I vary this T1 for some value. Small increments. Every time I keep increment, I collect the signal. Increment this, collect the signal. Apply pulse, increment, apply pulse, collect signal. Increment this by some other value, do this. Like that n number of experiments I do. Every time I increment this and collect the signal. And I am also collecting the signal at this place whenever I increment. Every time when I collect the signal, what is going to happen? I can create a time domain signal analogous to this one. This is what happens. You see, it is like this. Diagrammatically, this is what is happening. Look at it very carefully. This is a preparation period, evolution period and mixing period and detection period. Mixing period can be absent. I do not need to use it. That is optional. I am preparing. I am allowing the spins to prepare. Then I will put some delay T1. I will collect the signal. Initially delay is 0, no T1. I collect the signal. I increase T1 by some value, collect the signal. Increase T1 by some value. See here, it is moving. and then collect the signal. I keep on doing this. I increase it and again collect signal. See, look what is happening. Every time increasing the evolution time. What is happening for this one? That is constant. Detection period, that T2 is constant. I am not changing that. Only T1 period I am changing systematically. And then I collected the signal. So T1 is incremented systematically and the signal is collected for each T1 period. Okay, now how you look at it, pictorially you can see like this. This preparation period is constant. Here I keep on increasing the time and I apply radio frequency pulse and every time I collect the signal. This is always constant. This period I am not incrementing. Look at this one. Here there is an increment in the time. Evolution period is incrementing. This is how we collect the signal. But what will happen is, how do we get the 1 day signal in T2 dimension after each T1 increment? This T2 period I am keeping it constant. I told you I am collecting the signal in the last one. This is called T2 period. This is called T1 period. There are 2 time periods. This is evolution period is called T1 and detection period is called T2. Remember T2. T2 is constant. Only T1 is getting varied here. I keep this constant, collect it, do the signal. Now increment the T1, collect the signal in the T1, do the Fourier transformation. There are some phase distortions. Increment, do the Fourier transformation like this. Different T1 periods, I collect the signal. This always kept constant, but here you see phase is getting changed. Different T1 period. Started with 0 millisecond, kept on increasing delay and every time you see the phases are changing. What I am going to do is, I will do a trick. I will take any one of the signals here. For example, this carbon, this proton, and then measure the intensity and phases of that particular peak for all the T1 values and plot it. For example, take this one. This signal is positive, half negative, 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 again a positive. So it starts with like this. Intensity also is changing. Starts with negative, goes positive, changes, intensity changes. So there is oscillation going on. What is this oscillation? Similar to this one, decaying function, oscillatory and decaying function, time domain function which is decaying. And typically if you collect not 1 or 2 points, about 100 to 120 to 512 T1 points will do, collect a single data file, and then what is going to happen is, we create an FID in the T1 dimension. It is pseudo FID. Artificially we create an FID. For each T1 period, if you collect the signal and do Fourier transformation, we get a series of 1D spectra like this. A series of 1D spectra for each T1 point. But look at it now, intensity. Is it not oscillating? It is going like that. It is an oscillatory function. Okay? And this period is always constant. Here it is another time domain. As if you are collecting the signal and do a Fourier transformation for series of 1D, you see it is an oscillatory function. And this what is? The phase of the signal is systematically changing with T1. That is what is happening here. Alright, we will go further. We will see the plot of the signal intensity for a peak as a function of T1. How it is going to happen. And this is an interferogram. This signal oscillating here like this is like an interferogram, time domain signal, similar to what we saw in the T2 period. Okay. It is what we did, we created a pseudo FID. A pseudo FID is created similar to FID which we have collected the signal in the T2 domain. So what did we do in the 1D NMR experiment? It is a one time domain point, single Fourier transformation, single frequency spectrum. It is a one dimension NMR. When in the other case, we have 2 time domains. Then what we have to do? We have to do Fourier transformation for both the time domains to get the frequency domain spectrum. That is what I explained to you when I explained 1D NMR. Since we have 2 time domains, we do 2 Fourier transformation, you get a 2 frequency domain spectra. Remember, 1 time domain, 1 Fourier transformation gives 1 domain spectrum, that is single domain NMR spectrum. 2 time domain, double Fourier transformation, you get 2 frequency domain spectrum. That is what is going to happen now. Look at this one, how it happens. We collected the signal like this. That's what I showed you. This is T1 point. Now I'll do the Fourier transformation along this axis. Which axis? For the F2 axis. F1 is still a time domain point. I get frequency here. Here it is time domain. I'll go further. I'll do the Fourier transformation both in this dimension and in this dimension. This is the T1 dimension, this is a T2 dimension. Also called F1 dimension, F2 dimension, frequency 1 and frequency 2. Also called omega 1 or omega 2. Whatever they also called direct dimension and indirect dimension. This is what the nomenclature which is used. Okay. So, but now what I did is I collected the signal, did the Fourier transformation first in this dimension, and then afterwards I did the Fourier transformation in the other dimension also. Then we are going to get frequency spectrum in both the dimensions. That is interesting. We got the frequency spectrum in both the dimensions. This is a two-dimensional frequency domain spectrum. You got the point? It is a two-dimensional frequency domain spectrum, we got it. Then how many dimensions we can have in NMR? So far I told you about 2D NMR, 2 dimensions. How many dimensions we can have like that? We can have any number of dimensions, but there is a limit for it. For example, consider this one. I apply one pulse, collect signal in one time domain and do the frequency in one domain, you get one dimensional NMR. This is 1D NMR. One time domain, one dimensional Fourier transform, one frequency domain Fourier transformation, you get one dimension frequency domain spectra. This is one dimension. So, one time domain is one dimension. We go to this one, it could be homonuclear, heteronuclear, doesn't matter. Here I have one time domain T1, here I have another time domain T2. There are two time domains. This is called two dimensions. Dimensionality in NMR is different time periods, different time domains. You can have one time domain here, one dimension, dimension for as a function of time, other dimension as a function of time, like that. This is one dimension, this is two dimensions. Go further, you have T1 here, T2 here and T3 here. This is three dimensions. This is 3D NMR. 3 dimension gives rise to 3D NMR. So, what defines the dimensionality in NMR now? You have already understood with this, whatever I discussed. Meaning, a pulse sequence in an experiment which I am going to explain soon. A pulse sequence with n time periods, if you consider. Time periods is T1, T2, T3, etc. They are all given like that. T1, T2, T3, they are all different time periods. If I have a n time periods with n minus 1 incremented, n minus 1 systematically we increment to create a pseudo FID. And then only one of them is kept constant, one of the dimensions. So, after the n time domains, n minus 1 is incremented, only one time domain is kept constant. This gives rise to n dimensional spectra. So, dimensionality is defined by the number of time domains, time periods you have. So, T1, T2, T3, etc. you can have n number of time periods, and you can as well have 2 dimension. 2 dimension means 2 time periods, 3 dimension means 3 time periods, 4D means 4 time periods. Of course, you can extend like this. Beyond 5D and etc. is very difficult because signal will decay. Theoretically is different, but practically you cannot have more than 5D or 60, etc. 5D you can have, but beyond that it is very difficult. So, you can have different dimensionality in NMR. You understood? What is the dimensionality? Dimensionality is defined by the time periods. So, what defines the dimensionality? If you go further, a pulse sequence with n time periods gives n dimensional data, time domain data. Pulse sequence with n time periods gives n time domain data, and you do n dimensional Fourier transformation, you are going to get n dimensional frequency spectrum. Understand the logic now? You can have a pulse sequence with the experiment, different pulse sequences. If there are n time periods, you get n dimensional time domain data. You do n dimensional Fourier transformation, you get n-dimensional frequency spectrum, and this is called NDNMR, n-dimensional NMR. You understood what is the n-dimensional NMR now? So n can be anything. N can be 2, 3, 4, 5. If n is 2, you have 2 dimensions. N is 3, you have 3 dimensions. Okay. And how do you get the 2-dimensional spectra? Just for an illustration purpose. We can have different type of experiment called resolved experiment, correlated experiment, like that. As we go ahead, I will discuss all those things. Resolved experiment, I will resolve 2 parameters in 2 different dimensions. Correlated experiment, I will correlate 2 information in 2 dimensions. What is a type of spectrum? You see, you are plotting the spectrum. This is called contour plots. No, I'm sorry, stack plots. You are plotting this 1-dimensional spectrum like pattern in different stacks like this. Different stacks are there, stacked one above the other. This is called a stack plot. This is the way people used to do the NMR, record the NMR spectrum when the 2D NMR was discovered in late 70s or early 80s. Soon it has been replaced. Now this type of representation of the 2D data is not done anymore. Just I am trying to tell you this was the way it started with, it's called a stack plot. But now what is the way it is done is called contour plot. This is a stack plot, this is a contour plot. Same thing is represented as a contour here. Can you see any difference here? Look at it. This peak is put as a contour, different circles, one within the concentric circle, several circles are within that. Look at this peak is here. This strong peak is here. And these 4 peaks which are the stack plots, see several number of spectra are there here, you see, they are plotted like this. So many 1-dimensional spectra like that are plotted. And the same thing is put as a contour here. Each contour corresponds to particular peak in a stack plot. And this is F1 dimension, omega 1 dimension, and indirect dimension, F2 omega direct dimension. And all the time nowadays, you don't represent the signal or spectrum in stack plot. Everything is a contour plot. So what the 2D NMR you are going to record, the spectrum of 2D NMR is nothing but a contour plot. It is a 2D spectrum. It is nothing but this one transformed into this. Then you may ask me a question, how can I transform here to here? I will give you an analogy. Try to understand this. How do we translate stack plots into contour plots? Okay. See, look at this one. I have a stack like this. Go to the bottom. It is like a mountain, steep mountain. Go to the bottom. Go one round. Measure the area and put a circle. This is a contour. Go slightly above in the mountain. Go slightly above. Go one more round. Measure the area, and this bottom area's circumference is much more compared to the next one. Put another circle which is within this. Go slightly above. Measure the area. Put this within this. Go slightly above. Put it like this. Go above like this, like this. And what we are doing? We measure the area of this contours at different places and convert it into a contour like this. So the contour is nothing but the area of this peak. If you take the area of this contour, it is nothing but the area of this peak. That's all. It just imagine a steep mountain. At the bottom you go one round, put one circle. Go slightly above, come back one circumference, measure the area, put one. Like that you can keep on going to different heights. Every time you measure go one circumference, measure the area and put a circle like this. This is how we translate a transform stack plot into contour plot. Alright. So the area of the contour provides the integral area of the peak. That's all. This is how we convert a stack plot into contour plot. Now the question is, what is the time constraint in higher dimension NMR? You may ask me a question, hey, I want to do a 2D NMR, 3D NMR, 4D NMR. But you should understand before doing any experiment, what is the time constraint involved? How much time it will take to do an experiment? Based on that you have to decide your experiment. Say for example, 1D NMR nowadays in the present day spectrometers is less than few minutes. 5 minutes proton NMR, 10-15 minutes for carbon 13 NMR like that. Forget about exotic nuclei like nitrogen 15, etc. It will take more time if it is not labeled. But by and large, 1D NMR like nuclei like fluorine, phosphorus, and proton, they are all very fast. If you go to 2D NMR, it may take several minutes. There are 25, 10, 15, 20, 30 minutes like that. Go to 3D NMR, it will take several hours. Go to 4D NMR, it may take days. If you go to 5D NMR, it will take several weeks. That means if you have to do one experiment, you have to spend several weeks. And what is the cost of the NMR instrument? Cost of the NMR instrument runs into several crores. 800 megahertz may be about 15 crores. When so much of money has been invested, nobody will give you 1 week or 2 weeks or 3 weeks to do an experiment. So it is the judicious you have to decide depending upon the information you want to derive, whether you want to do higher dimension experiment or not. So there is a time constraint. So measurement time increases exponentially with increasing in the dimensionality. All right. And also what will happen as the dimensionality, the measurement time increases, sensitivity also decreases. It goes by square root of the measurement time. Sensitivity goes by square root of the measurement time. And dimensionality also depends upon the size of the molecule. You cannot take a small molecule and do 5D NMR. What is the use of that? If you want to do a n-dimensional NMR, multi-dimensional NMR, it depends upon the molecular size. For example, a molecule size of let us say few kilodalton, 20 to 30 or so, just 2D NMR will do. Around slightly more than that, 30, 40, 50, 3D NMR. Slightly above 40 or 50, 4D NMR. If you go to 50, 60, 80 or 90 like that, you not only you need 4D NMR, you need additional experiment like deuteration, TROSY, etc. So dimensionality of NMR depends upon molecular size also. So increased information will be there when you have increased dimension because of increased resolution. That I am going to explain. So how do you choose the required dimensionality for any given molecule, etc.? We will discuss in the next class. Right now, since the time is getting over, I don't want to continue further. But in this class, we started with understanding what is a 2D NMR. What defines dimensionality? I said dimensionality is defined by the time. An experiment, a pulse sequence with n time periods, with n minus 1 incremented, only one time and domain is constant, is going to give n dimensional NMR. We have n time periods, n dimensional Fourier transformation you do and you get n dimensional frequency spectrum. And most of you can have a different way of representation of the 2D data. It was stack plot and contour plot. Stack plot is outdated. I showed you how we can use the contour plot. Contour plot, area of the contour is nothing but the integral area of the peak in the stack plot. So we can use that. And of course, dimensionality of NMR depends upon how much time constant is there. I explained to you. 2D NMR may take few minutes, 3D NMR may take few minutes, or let's say few 1 or 2 hours, 3 hours, 2 hours like that. 4D takes days, 5D takes weeks. And also resolution enhancement and sensitivity depends on goes by the square root of the measurement time. So there are certain restrictions also involved in this thing. So it and also depends upon the molecular size. That also I explained to you. So what is the size of the molecule you have to use for getting the different dimensionality. But the question is, how do you choose a required dimensionality for a given molecule? That we will discuss in the next class. Thank you very much.